Right now, in this unit now, we're going to deal with the petrochemical industry, okay? That's very important, very popular in exams, you need to be careful. And in the last unit I'm going to do with you, we'll deal with petrol itself and the octane number. So the things you're focusing on now are knowing your hydrocarbons, being able to draw them and have structures for them and identify them, first four members, this unit, and that's what you'll need to prepare for your forthcoming exam. Okay, very important. We're now on page 4 of your notes, and I'm reminding you again, please, this is page 4. If you don't have them at the moment, again, pause the video, please, go away and print them out, please, and come back and continue. Okay, very important that you have that page 4. All right, now polymers are on the left and the petrochemical industry is on the right of that page. Now, I really don't need you to do much on polymers. I've only mentioned them in passing. You're not going to be asked many of them at all. In fact, there's only 3 there, and I prefer to wait until all the organic chemistry was complete before doing anything with them. Now, please don't even take any of this down. It's there on the side, one side of your page, but I would like to think that you could work on them and that you have something to go on their polymers, okay? They are basically long carbon chain molecules formed from smaller ones called monomers. Mono means one and poly means many. So if you have certain molecules that can join together, you're going to get a polymer. And of course our lives are full of polymers now, okay? We synthesize all sorts of polymers for all sorts of reasons. The only 3 of consequence to you that you would need to know about would be listed there for you. I'll mention them to you. Polythene is one of them. Polyethene, that's ethene, and that's polyethene. Now I need to give you some idea as to what happens there when we talk about polymers. I hope you can hear me, guys. What we need to be aware of is when you're dealing with this, that you're working through a system here that allows you to cover this, okay? Now, so if you had a molecule with a double bond, okay, double bond, 2 bonds, and if you could imagine a whole series of them in a line like that, how would they join together? And the answer would be simply that you break one bond and they join next to them. So if you had a whole load of people standing like this in a straight line, they could easily join hands like that to form a very long chain. And that's exactly what happens. The monomer has a double bond, the bond splits that way, and they form a long chain. And that's exactly what we're talking about here. Under the right conditions, that will happen. And that's known as addition polymerization. That's fine now. Don't worry too much about it. You just need to be aware of that. That one is important for you. There's the monomer. I've left out the H's, of course. You always put in the H's last. And there's another one, propene. There's 3 of them there. 1, 2, 3. Propene. And if you polymerize that, you get polypropylene. Polythene is generally used for packaging or damp proofing under floors or wrapping generally, okay? And polypropylene, well, every plastic toy is made of polypropylene. Okay, that's fine. There's other ones there now, you won't need them, don't worry about them, that's fine. That, like this one is PVC, that's vinyl chloride, and so that's polyvinyl chloride used for making pipes. Okay, and gutters and things like that, and windows, okay, PVC. Now, you won't need them, and they come up in another part of your course, so don't worry. There is, if you like, the starting block, whatever the X might be. The X might be a H, as it is here. The X might be a CH3, as it is here. Or the X might be a Cl, as it is there. So you get different polymers depending on the monomer you have. And that's effectively the only bit I need you to know about that. Don't worry about anything else on the page. I think that's fine. Top right hand side of your page there, you have the 2 polymers you want. You have these 2, and they're there for the moment. So I'm going to start then on the petrochemical industry, and we'll just have a look at what you need on that. Okay, now we're starting with the idea of petroleum, and I think I'd need you to be aware as to what's happening there. Let me deal with that next for you then. Petroleum. We'll go through all of this in due course now, don't worry about it, but will you take it please? We need to make sure everything is all right. I have a bottle of petroleum here, okay? That's crude oil, okay? It's a thick, tarry liquid. And I'm just mentioning to you now, I have no idea what it's made of. Okay? Crude oil is a mixture of long chain hydrocarbons. And we're talking 40, 50, 60, 70 carbons in a chain. We don't know. Okay? But there's a mixture of them. And in its present format, it is fairly useless. Okay? That's basically it. It says in your notes, petroleum, also called crude oil, is a dark, viscous liquid which is a mixture of a large number of hydrocarbons. Okay? Long carbon chains, in other words. This raw material is the result of decayed plants and animals over millions of years. And I think I'd want you to write in there at the end of that sentence, over millions of years, fossil fuels. Okay, decayed plants and animals over millions of years, fossil fuels. That's a fossil fuel, very important, okay, that you have that. Now, in its present form, it's fairly useless, and I'm just mentioning that to you because our chemistry is about how will we make it useful. Okay, now you probably know the green agenda is we're trying to move away from petroleum anyway, but that's neither here nor there. We need to know its origin and its chemistry, and you have to be aware of that. To refine petroleum, a number of processes are used, and there's 3 of them in all which we'll be going through, and I'll be giving you these in detail now. The first one is called fractionation. Written there in your notes, A is fractionation. Will you qualify that, please? It means, fractionation means separating the mixture petroleum. Petroleum is a mixture, and fractionation is the separating of it, okay? And you're basically separating the parts in it. That's fractionation. The second step in refining petroleum is cracking. And that means literally cracking a long chain into smaller ones. That means making the long chain shorter. Would you write in after cracking, please? Making the long chain shorter. And the third one, reforming. Now, there's an open debate on what reforming is, but I want to tell you, it takes a molecule of one particular shape and reforms it into a different shape. Generally speaking, long chains into cyclic compounds, into rings. But it could also be into branches, or there could be other which I'll deal with. I'm going to deal with these in detail now, so don't worry at all about them. And that's very, very important that you will deal with that. Now, what I'm going to do next with you then is I'm going to go through each of them in turn and elaborate on them. Now, you need to be comfortable with this, and there's a few facts here you'll need to be able to volunteer when you're finished. Now, I did say this to you that I don't like the idea of rote learning. If you have any kind of association of the idea with something, it makes life very easy. And I'd like to think you would be doing something like that. So I'm starting now with fractionation in your notes. And it says there in your notes, this is the separation of the crude oil mixture by fractional distillation in a fractionation tower. And there's an expectation now you'd know what a tower looks like and how you would use it. And I have something like it illustrated here for you, and I'm going to talk to you about it then, but we need to have a look at that first and see that it's okay. All right? Now, just take a look here at what we have now. Basically, these are all the fractions. The one at the bottom is residue. Okay? The next one is gas oil. The next one is kerosene. The next one is Nafta. The next one is light gasoline, and the top one is petroleum gases. Now, I'll ask you to add them into your notes in due course, all right? Gasoline won't do. You must write the word light gasoline in front of it. Okay? And up here, gases won't do. You must call them petroleum gases. So you must write in the word petroleum. Now, I'm going to ask you to kind of be aware of some of this. You don't need to deal with anything here now other than this is fractional distillation. I want to give you some ideas to what you would do. There's a technique in chemistry called fractional distillation, which will separate 2 liquids that have different boiling points. Now that's very easy. For example, if you wanted to separate alcohol and water, you'd put them into a flask like that, the mixture, and you'd heat it. You'd have a thermometer here, okay? And you'd heat it to a particular temperature. And then you'd collect, what would happen is you have a tube here, and you'd collect the first fraction by heating it to the boiling point, at the lower boiling point. Alcohol has a boiling point of about 80 degrees Celsius. Water has a boiling point of 100 degrees. If you had a mixture of alcohol and water there, such as something like wine now, and you started heating it to 80 degrees, then all the alcohol would evaporate at 80 degrees, but none of the water. So it's very important you recognize now what's going on there. You're separating this mixture of petroleum. You're separating this based on the fact that you have different molecules in there. They have different masses or lengths, and they have different boiling points. And so you heat it to different temperatures, and you'll produce different parts of the mixture at that. So what would happen here is the first fraction, that's what they call them. The first fraction would be alcohol. Okay, that would come out in here at 80 degrees. And when no more liquid was coming over, then what was left behind would be water. Because obviously at 80 degrees, the water won't evaporate. And that's the whole principle of this then. Now, it's a logical deduction, I hope, for you to say that the bigger the molecule, the higher its boiling point. When you boil something, it's basically liquid particles that are going to take off into the air as a gas. And if they're very heavy, needless to say, they'll be harder to boil. So you need to raise them to a higher temperature. So heavier molecules, generally speaking, have a higher boiling point. And that's exactly how it works here. Now, this is the, basically, I'm going to draw this, this particular separation unit for you, okay? You need to be aware of it now as a unit. We'll talk about it later in terms of what it would look like, but we have to look at that, okay? And I'm going to draw something for you here now. This is a fractionation tower in its very simplest form. Now, bear with me, please, and note my artistic talents. Okay, here we go. A container like this is what you need. Okay, a chimney on top. Okay, a base here. Okay, a base here with a lock on it, and the petroleum comes in here. Okay, you have a furnace here. A furnace is basically a glorified heater. Okay, a flame burner there which will heat that, and the petroleum comes in here. Petroleum comes in here. Now you have 4 floors on this building. Just keep it very simple. 4 floors. There's 1, there's 2, there's 3, and there's 4. Now, you will get 6 fractions with that. Now, I'm drawing this because I'm putting myself in your position. This is exactly what you'll be doing in the exam now. You'll be drawing the fractionation tower. Fractional distillation goes on here. Now, the furnace is down here, so the hottest part of this tower is at the bottom. I'm going to write 350 degrees down here. 350 degrees, and I'm going to put 40 degrees up here. Okay, obviously if you have a fire in the hearth, the hottest part of the chimney is at the bottom, and as you go up it gets cooler and cooler and cooler, right? And that's exactly it. So what will happen there is the petroleum is brought in here, there's flames here going to, I should be making that bigger for you, okay? They're going to vaporize that when it comes in here, and the vapors are going to rise up here. Okay, they're going to rise up like that. Now, those with a boiling point at around 300 are going to stay here. And that'll be the heaviest fraction, okay? So we talk about the bottom being the heaviest. And the top will be the lightest fractions. Then this, I'm going to say roughly now, this is 100 degrees here, and this is 200 degrees somewhere here. Okay, you're getting the general idea. So the mixture vaporizes, and as it moves up through this particular tower, when the vapor strikes one of these shelves, which has a temperature equal to its boiling point, then that particular fraction will condense onto that particular shelf. And so what will happen is you'll get different molecules at each shelf, and they'll be taken off as different fractions. So you have a total of 6 fractions. Okay, now I better repeat that again just to make sure you're okay. You take this gunge, this mixture of anything and everything, and you heat it to a very high temperature of about 350 degrees. That's the highest a naked flame will get you. Okay, and much of it will vaporize at that. The smaller molecules have a very low boiling point, so they'll go right to the top. The simple rule is this: if something had a boiling point of 200 degrees, when it would strike that shelf, it would condense. If something had a boiling point of 100 degrees, when it would strike that shelf, it would not condense, it would stay as a gas and it would move up to the next one and the next one until it reaches a shelf which has a temperature equal to its boiling point. When it reaches a shelf with the temperature equal to its boiling point, it condenses. So you're going to get the different fractions condensing onto these. Okay, like that. Now, I could draw more about this for you. It's not a simple matter of a hole in the middle. There's caps over them and all that, but they fill up. And so you'll get your various fractions here. And so you're asked to name the fractions. The one at the bottom is called residue. I better write them carefully for you now. You're expected to know these now. There's no excuse for not knowing these. This is residue. Okay, the one at the bottom is residue, right? The next one is gas oil. Okay, I've got to write it in here. This is gas oil. I'll come back to them in a moment now, but I need you to know. You must know the name of that. The fraction here is gas oil. The next shelf there is kerosene. Kerosene. Kerosene is there. Okay, kerosene is there. The next fraction is Nafta. Mind the spelling, please. N-A-P-H-T-H. Nafta is in there. The next fraction is light gasoline. L-I-G-H-T. Light gasoline. Now, are you all aware that the word light here means not heavy? Okay, nothing to do with illumination, okay? Light gasoline. The light fractions are up here and the heavy fractions are down here based on their boiling points. And lastly, at the top, you have petroleum gas. Petroleum gas. And because it's a gas, it'll escape out through the top things and go to its own storage unit then. So you're going to end up with 6 fractions. This one is taken away at the bottom here, the sump. This one is taken out through pipes to storage tanks. So each of them go to their various storage tanks. Now, what are you expected to know? You're expected to know the 6 main fractions that petroleum breaks up into. How much of that, how much of that, how much of that, I've no idea. It will depend on what the petroleum is. Did it come from the North Sea? Did it come from Saudi Arabia? Did it come from Texas? You getting the idea? There could be different compositions of crude oil depending on where it came from. But we know they all contain some of each of them. And there's 6 of them there now. You must know the 6 and you must know them in the right order. And wait for it, you must have at least one clear use of each. Now your notes has listed it. I've only a table there now, I've no drawing. It would be well worth your while in your own time to do a bit of a sketch on this, just to get a sense of what everything is. Remind what I said, this is a building. It has 4 floors, it has a chimney, and it has a sump at the bottom. It has an outlet at the bottom. So fraction 1 comes out here, fraction 6 comes out there, and they go out to their storage tanks in their various ways, okay? So you have 6 fractions in all, right? And you must know their official names now, that's very important. What is the reality then? The heaviest fractions are down here and you'll have carbon chains here over 25 carbons. Now, the middle column in the table in these notes is not important. You don't need to know the exact length of these chains. What you need to know, however, is that this is a longer chain than this, which is a longer chain than that, and the chains are getting shorter as you go up. That's very important. The number of carbons in the top one is 1 to 4, so it only goes up as far as butane. Okay? Normally, Calor gas would take the top fraction there. They would make bottled gas from that because they're the small molecule. They're the most expensive as well, by the way. Okay? And that's very important. That you'd be aware of that. So they're called light fractions up here, and they're called the heavy fractions down here. Based on the premise that these have the highest boiling points, and these have the lowest boiling points, and consequently, you have smaller molecules here, you have much bigger molecules here. Okay? And that's very important. So your right-hand column is the use of these now. And everybody needs one clear use of each of the 6 of them. Okay, and I said specifically there petroleum gas, and its use of course would be LPG. Do you know what that is? That's liquid petroleum gas. They liquefy the gas to deliver it, and you turn it back into a gas when you burn it. Bottled gas, in other words, is LPG. That's that one, okay? That's that one. Next, light gasoline. Are you aware, everybody, that the Americans would tend to refer to petrol as gasoline, gas? Yeah? So petrol would come from that. Very good. Petrol. Okay. Now the next one then is Nafta. Now Nafta also produces petrol, and they may ask you something like this now. They may ask you something like, name the fraction from which petrol is produced. Okay, so you must know this table. You must know that table now. The idea of kind of having a passing knowledge or a jumbled up idea of it won't do here. You must know that table. And I can't do anything for you now. You have to learn it. You have to try and associate them correctly in any way you can. Naphtha is also used for making plastics. Maybe you need to write that in if it's not there already. Plastics. Your polymers are generally made from crude oil, and that's the fraction they'd use to make them, of course. Yeah? That's the best one for petrol, by the way. That would also do, but that's the best one for petrol. Now, kerosene. If your home is heated with oil, then you're probably burning kerosene. So heating, central heating would be the main use of that. Now, you qualify the word heating if they asked you. Heating wouldn't do, okay? You'd have to say central heating at home, or heating a home would be fine. Or they also use it for aviation, right? They also use it for jet planes, or, okay, the jet engine. The jet engine is used for kerosene, okay? That one has an additive to it so that it wouldn't ignite prematurely. But don't worry about it. I'm saying it is kerosene, okay? Kerosene is the one we use for our heating. Now, gas oil. Gas oil is an official name for diesel, I think we'd want to be aware of that. It's an official name for diesel, okay? D-I-E-S-E-L. Diesel is taboo now, as you know. They're trying to do away with it. It's a polluting fuel, but basically that's diesel. If you were to purchase some diesel, the invoice would say marked gas oil. If we call the diesel marked gas oil, meaning it has a dye in it for road use. Okay, there's a different dye just for agricultural use, but its diesel would be the one there. And the residue at the bottom, of course, is used for all sorts of tarmac. It's a very cheap fuel, right? And it's used for all the things I've listed there. Grease, roads, okay, covering roads with tar, tar, bitumen, okay, bitumen would be used here and all them, okay, bitumen. B-I-T-U-M-E-N, bitumen, etc. Okay, that's a rough crude. That's the cheapest fuel now, fairly useless. It's used for roads and maybe roofing. They might seal roofs in certain places by melting tar onto it. Okay, so that would be a way around it as well. Now, I don't think I could do any more for you than what's on the board at the moment must be well known. Now, please take your time with that, but you do need to do it. You have a table in your notes, but you need to construct that again now. You need to be very clear as to what that's about. And I'm hoping that that will make sense. I'm going to say it once again out to you. When you're doing this a simple table, can you list the fractions you get from crude oil from the bottom up? Residue, gas oil, kerosene, naphtha, light gasoline, and petroleum gas. Now, I don't know what you're going to do. We all have our own mind games we play to get that right, but you'll have to remember them, okay? And they have to be in the right order now, okay? You'll mix them up. And you have to have at least one use for each of them. One will be enough, but you need one use for each. That gives you bottle gas, that gives you petrol, that will give you plastics, that will give you central heating oil or aviation fuel, right? This one here, the gas oil, is diesel for trucks and machines and, okay, generally for engines, right? And residue, anything and everything, it's a tar. It's a bunker fuel as well. Ships often run, they use huge amounts of fuel, so they run on a cheap fuel, and it's often called a bunker fuel. But basically, tar for roads or bitumen, roofing, and any other one you're there. But you need one that will... Now, certain things, due to your own life's experiences, resonate with you. And you know, will you pop into them immediately? Name two fractions you would get in the fractionation of crude oil and give the use for each of the fractions you've named. Okay? Now please, can I make a suggestion to you? Only if you're asked, don't volunteer residue. Residue is too loose altogether. It's the leftovers. Okay? Use two of the others above. You'll be clearer on them in every way. Now, there's nothing wrong with that, other than residue is a very loose name. A residue in chemistry means when you filtered something, what's left behind. That'll be left behind. Why is it left behind? Its boiling points are higher than 350. The molecules are so big that it's higher than 350, so obviously it won't vaporize. And it's left there as a gooey, oily tar at the bottom. Okay, whereas all the others will condense onto the various shelves. Now, can you remember what I said to you? It's a building. It has a basement to it, and it has 4 floors, and it has a chimney. You're worried about me, are you? You know what I'm saying? That you need to have a sense of how will I remember this without having to rote learn it. Now, you must practice that. You need to draw that sometime in the next 2 days. And not immediately now, because it's short. Leave it go and do a doodle someday and see how much of that will you get right. You would be pleasantly surprised. Now, you must have all 6 because they could ask you about any one of them. And that's vitally important you would do that, okay? So there's a furnace down here. Maybe I'd put the furnace a bit lower, but all the crude oil comes in here. They heat the hell out of it. Some of it vaporizes and goes up through the column. And when that part of the mixture strikes a shelf, I'm calling it, which has the same temperature as its boiling point, that part will condense onto the shelf. And then it's taken away to a storage unit, so you have 6 fractions. One here, one, and one out the top. So 4 floors, a basement, and a chimney. Just to remember them, will you keep that in mind, please, when you're doing that, and you'll find that's very good. Now, where are we going from here? Now that we have the fractions, there's an expectation that you know the economics of it. And on the top of page 5 of your notes, then, can I just say to you, then, it says there clearly, the products of fractionation yields an oversupply of the heavy fractions and an undersupply of the light fractions. Okay, so we get too much of this and we get not enough of this. Or to put that another way, there's a high demand for the ones up here. There isn't much demand for the ones down here. So the chemist has to go to work on resolving that. Again, you get too much of the heavy ones at the bottom two maybe, and you don't get enough of the top ones. By the way, that's why petrol would cost a lot more than diesel. Okay, we're based on that premise. It is not. It's actually government tax, but don't worry about it. Okay, but the idea is that, generally they're not as valuable as them. By the way, they're dirtier fuels as well. If you were burning them, they're dirtier. They're cleaner as you go up. Okay, the cleanest fuel will be coming out the top there probably as methane even. Okay, so you'd have to take it that with the case, right? To deal with this problem, the heavy fractions are cracked to produce lighter ones in the presence of a catalyst. So what you do is, we have too much of the long chains. We haven't enough of the short chains, so we're going to have to break up or crack up some of the long ones to make shorter ones of them. I want to show you just one chart with that. That might be useful. Let me just turn your life around here for a moment and see, can I make sense of that? There's a little chart. I hope you can see it. Okay, I'll talk my way through it for you. Okay, that is just the whole principle of it now. There is the more sophisticated version of that. Keep it very simple now, please. Okay, there is the basement. Look, there's the residue being taken out here. There is the crude oil coming in, and there is the base here. Okay, that's one. There's the gas oil coming out through this pipe, through on this shelf here. Okay, on this here, you're getting the gas oil. There is the next, look, that is the kerosene coming out here. There is the naphtha coming out here, the naphtha coming out there, and there is the gasoline coming out here, and there's the petroleum gas escaping through the chimney on top. Now, it could be very sophisticated. Keep it simple. That diagram is much better than that. Modesty prevents me going any further. Okay, keep it simple and then it's clearer. Don't be trying to do that. And just look some of the illustrations there for you. Can you see? That's camping gas or welding gas, which is the gas, the petroleum gas. Next is gasoline. There's a car and there's a little light aircraft. Next, there's naphtha and all the plastic products there. There's kerosene, there's a radiator, a heating radiator, and there's a jet plane there. Okay, next you have down here the gas oil. I see there's a locomotive for a train run on diesel, there's a taxi, and there's a truck. Okay, and you can see at the bottom all the lubricants there for dealing with that, road coverage, bitumen, and stuff like that. Okay, so it's important that you're able to deal with that more than anything else and that you have a sense of what it's about. Generally speaking, that's not a problem. You just need to be aware of that when you're working through it, and it'll be fine. Now, I'm going to leave that for the moment because what I need to do with you now is we need to look at the whole principle of, we're down here now with this catalytic cracking. Okay, and our problem now is I'm going to have to get rid of this. I'm asking you to be aware of that. I need to get rid of this, but before I remove it, will you all accept, please? You must be able to reproduce that. Okay, now cracking, and we need to mean what cracking is. Cracking means you have a long chain and you must reduce it into shorter chains. That's very, very important. Right, now, you have support notes on this now, so I have no problem with that. I'm expecting you to edit the notes as we go along, okay? And there's no problem here. Cracking then, its official name is catalytic cracking. In other words, cracking in the presence of a catalyst. The catalyst used will be a mixture of oxides of aluminium and silicon. They're the catalyst used. The products of cracking are one of the following. It'll either be a gas mixture, they're the short chains, right? Or a liquid, a branched alkane, such as petrol, or a residue of a fuel oil. Now, please, that's very loose, and I don't think you need to worry about it. Now, here is what we need to do next. We need to illustrate an example of cracking. And I have drawn in your notes, a carbon chain which is 16 carbons long. And they would ask you to suggest possible products of that, or they might dictate products to you when it undergoes cracking. And I'm going to try and do that for you because I think it's very important. 1, 2, 3. I put 16 in that one. 4, 5, 6, 7, 8, 9, 10, 11, and 12. I'll settle for 12, okay? That's all right. I'll settle for 12. I just need to give you the idea as to what we're going to do. Okay, there's one carbon chain in the petroleum mixture. Let me go for 13. Okay, that's fine. Let me go for 13. That's good. There's 13 carbons there. I'll write that down now so that we know we have 13 carbons. Okay, 13 carbons. What will happen when you crack that? Now, in the presence of a catalyst at high temperature. at high temperature, that's going to split into pieces, okay? Now don't worry too much about the catalysts. Their name there is oxides of aluminium and silicon. That's not important, okay? I'm basically going to tell you the rules for this now. You're going to chop that up into pieces, and there's a few very simple rules, okay? And the rules are as follows. The number of carbons you start with must be the number of carbons you finish with. Are you okay? Very important now. So 13 there must break up into that. Next, everywhere there's a crack, there's a double bond. I think they're probably the two base rules you must have now. And I'm going to do that for a start for you now. Now, look, if that's 13, I would hate to think you would write a 4, and a 5, like two identicals. Try and make them different if you can. That's not always possible to still be right, by the way. I'm going to go for a 3 for a start. Here we go. A 3. Okay, I'll go for a 4 next. 1, 2, 3, 4. That's 7. I'm going to go for a 5 now. What will that give me? 5 and 4 is 9, 9 and 3 is 12. No, I'm going for another 3. Okay, the bigger the number you have, the easier for me to vary them. That's 6 and 4 is 10. And that's a final 3. That won't do, folks. I'm going to cheat here. I'll put in another one. And I'm putting in a 4 here. Now, I'm only doing that to point out to you that this is random. Okay, this is random. Now, what I'm going to do, sorry, before I do anything now. Okay, I have 14 here now. 2, 4, 6, 8, 10, 12, 14. I have 14 there. I have 3 and 4 is 7, 3 is 10 and 4 is 14. Good? Okay, try and not end up with 12 and break it up into 3 4s. Okay, now this is analogous now to dropping a glass bottle on the floor and trying to predict the pieces you'll get. They're totally random. Are you getting that idea? There could be two identical pieces there. Unlikely. Okay? And remember, some of these carbons could be 50 or 60 carbons, chains could be 50 or 60 carbon long. So like the random breaking would be considerable. Okay? So try not to have regulars in it. Okay? But there'd be nothing wrong with them provided you obey the rules. Everywhere there's a crack, there's a double bond. There's a crack there. There's a crack there. There's a crack there. There is no crack here. Okay, there's 3 cracks to get 4 pieces. You didn't think I was that bright now. There's 3 cracks if you 4 pieces. If you 5 pieces, there'd be 4 cracks. So double, double, double. Have you got those rules now? They're not written anywhere for you. They're not written anywhere. Okay, you break it up into random pieces. You must end up with the same number of carbons when you finish as when you started. Very good. And you must realize there's a double bond for every crack. That's what you need. And so here we go. Double bond there, double bond there, double bond there. No double bond there. Now, every carbon has 4 bonds. Watch me. 4, 1, and 2. And 2. And 2. And this one. Be careful. Now, folks, I need to make sure that you can see them separately. Now, you'll be asked to name them. That is propene, P-R-O-P-E-N-E, because, of course, there is a double bond there. That is butene, B-U-T-E-N-E. This one is propene again, P-R-O-P-E-N-E. And this one, it has no double bond. It's an alkane. It's butane. B-U-T-A-N-E. Now, I've obeyed the rules. Have you got the rules clearly in your head now? The total number you started with was 14. There's 16 in your notes, by the way. Okay? 16 in your notes. Okay? Very important. And you break them up any way you like now. Any way you like. Chop them up into pieces so you have the same number of carbons here as you have here. But everywhere there's a crack, there's a double bond. By the way, that's the opposite of polymerization. Can you see what would happen? When the double bond would break to join with the molecule next to it. So you're going the other way now. You're breaking the molecule. So the double bond there, double bond there, double bond there, and there'll be 1. So if you had 5 pieces, you'd have 4 double bonds. If you had 7 pieces, you'd have 6 double bonds. If you had 12 pieces, you'd have 11 double bonds. Is that okay? And that's what you're doing there, nothing more than that. Look at what's in your notes then. We had, I've told you, 16 carbons there. And when they undergo catalytic cracking, they break up into 4 pieces. The first is a 4 carbon, the second is 5 carbons, the next is 3 carbons, and then I have a 4 carbon again. And you see there's a double in the first, there's a double in the second, there's a double in the third, but there's nothing in the fourth. Because you need a double bond for each crack. If you want 4 pieces, you need 3 cracks. And that's very important that you have that. Are you okay? And you must have the same number. So they're the 2 simple rules now. Have you got them? And it's not written anywhere in your notes. When you crack a molecule, The number of carbons must remain the same. They can't disappear. Must remain the same. And every crack has a double bond. There's no double bond there. They're 3 alkenes, and that's an alkane. And they're likely to kind of just ask you, to name a product you would get or whatever, okay? That would be it. Now, that's not very difficult, and I don't want to pretend it is. But you have to understand, you could start with any length of molecule, 56. They won't do that to you now, but I mean, just be aware of that. Simple rules when you're doing that. If they told you that the products consisted of an alkene, an alkane, and a branched alkene, then you'd have to look that piece, now that's for another day, not for now, you'd move that piece into there. And to be a branch, you see, to be onto the side. But I would draw that first, and then I'd put that in there. That's not likely to happen for the moment until you have the rest of the course done. But that's effectively what you're dealing with, and I hope that's okay. Now, that is what we are calling cracking. And why do we need to crack these molecules? We've too much of them, and we haven't enough of these. Okay, you see those ones now would fit up here in the top. You get more petrol then as a result. So catalytic cracking is the use of a catalyst to crack a long carbon chain into smaller ones for which there's a higher demand. Okay, as it happens, they're commercially more valuable as well. You'll pay more for the products up here than you will for the ones down here. Okay, and that's rather important that we know that. But once you're aware of that, you're fine. There'd be nothing at all to it. That's all we want then. And I'm going to leave it there for the moment. Now, the next thing we're going to deal with is reforming. Now, reforming is a bit like myself. It's a bit misunderstood. And we need to kind of qualify that. Sometimes the term dehydrocyclisation might be used. Can I get rid of that now? That's the end of catalytic cracking. Okay, that's the end of that, and I hope that's okay, that we can deal with that now. Can I bring you back to seeing that you're okay with that? Yeah, I'm just checking that you're able to see the board more than anything. This is the place you need to see mainly for most of my work, and I hope that that's okay, that we can deal with it like that, okay? Now, what I'm going to do here is, I'm going to mention to you now about reforming being called dehydrocyclisation. Dehydrocyclisation. Now that sounds a very complicated name. It's a very simple idea. We're going to get to it fairly quickly. Just bear with me while I wrap it for you, okay? Dehydrocyclisation or reforming would be more or less the same thing. This is the conversion of a straight chain hydrocarbon which are inefficient, okay? I'll be dealing with that in the next video, into, I have branch compounds there. Will you write immediately under branched into cyclic, C-Y-C-L-I-C, into cyclic compounds in the making of petrol. Now keep it as simple as that for the moment, will you please? Cyclic compounds. And ultimately we need to be aware of that reforming, right? I'll show you ones now in a minute, but we need to look at this first. So, dehydrocyclisation. Here is hexane. Hexane is C6H14. I'm going to draw it for you. There it is, okay? I better put in the H's this time for once. Normally the H's only go in at the very end when you have nothing further to add to it, okay? But make sure you get the shape right first and the H's go in last. Now, that is hexane, okay? And that's the shape of it, okay? It has 6 carbons. 6 and 6, 12, and 2 is 14, H14, and that's an alkane. Now, you could reform that, okay, by turning it into a cyclic compound, and what you get is cyclohexane then to become, basically we could make a ring out of that by simply taking the 2 ends of the molecule and joining them together. But if you do that, you need to remove the 2 hydrogens at the end. I better tidy them up for you. You have to remove these 2 hydrogens if you want to do that. Would that make sense? If I cyclize that and I make a ring of it, I need to kick out the 2 guys at the end. I would. And that's exactly what you get then. Okay? That's what you get. 1, 2, 3, 4, 5, 6. And there's the ring. And there'd be 2 hydrogens on each. 2 hydrogens on each is right. Okay, 2 hydrogens on each, and as well as that, the 2 missing hydrogens plus H2. And it's called dehydro because you're removing hydrogen. Dehydro is dehydrogenating. And they've abbreviated. Dehydrocyclisation means making a cycle of it, okay? And that's exactly what they do, and that's very important. Now, that'll be relevant in the next topic, which I'm going to deal with, and I'm going to ask you to wait till then to deal with that, okay? Because we have to be aware of that. And basically, isomerism will come up in the next one as well, and I'm going to deal with that there. Now, before I finish with that, I just need to remove this, and I'm going to show you something else here that I think you would need to see, might be useful. I have a chart here with reforming, I hope, and that you'll be able to see that now. There is a simple illustration of reforming. I hope it might be okay. Just checking it's visible for you, is it? And you'll have some sense of what that's about. Okay? And now, that's the one I really want to show you. There's the 6 carbons. You take out the 2 guys at the end and you make a cyclic. That's a better fuel than that, for reasons I'll explain in the next term to you now, okay, in the next unit, okay? By kicking out dehydrocyclisation. You could be asked to write that equation. Okay? You'd be writing exactly that now. That when you basically dehydrocyclize, this is what you do. There's the arrow. You take that molecule under the right set of conditions, right? And you turn it into a cyclic compound. You'll be putting in all the H's here, by the way. There'll be H's all the way around. Had I better say this to you? Had I better say something to you? Does anybody think that that's benzene? No. Benzene is C6H6. That's C6H12. Okay, that's called cyclohexane. That's called hexane. That's called cyclohexane. Hexane is C6. Can you read that? C6H14. 14. This is C6H12. Be careful. Cyclohexane has lost 2 hydrogens. Be careful. Now, you could well be asked to write that. Okay, that is known as, it's a form of reforming. There's other ways of reforming as well. Of course, you could branch something. You could take a piece of the molecule. And put it in here. Okay, and that's called isomerization. That's an isomer of that. You take a piece of that and you put it there. It's more branched, it's more chunky. It's yet less of a straight line, and that's very important. And sometimes the elimination of something from molecule is called reforming. But that's the main one you want. To be careful. These are all charts produced by Irish Shell, so you can see that they would have relevance to the petroleum industry, and that's rather important. Now, that brings us to the end of that category, okay? It would be important for everybody to be clear as to what that entailed, and that you would be clear down to that point in it. The next thing coming up in the next video now is, of course, petrol itself, all right, which we'll be doing next.